Today we're going to look at 2019 ordinary level physics paper. So question 1 asks us to look at mechanics, in particular laws of equilibrium. So the question states that a student performed an experiment to investigate the laws of equilibrium. She suspended a meter stick from 2 Newton spring balances and hung weights from the meter stick until it was balanced and level. Before setting the experiment, the student took 2 measurements. She measured the weight of the meter stick to be 2 newtons. She found its center of gravity at 50 centimeters mark. So, we have 3 questions related to the text above. The first question is, how did the student measure the weight of the meter stick? It's important to remember that the weight is mass times gravity, and it's a force, and that we have a reading of the weight in newtons. So it's a force, and the weight is equal to mass times gravity. So if we want to answer this question, simply we need to say that the student either used Newton balance, and Newton balance gives you a reading in newtons, or the student used an electronic balance and multiplied the mass times gravity. So to get full marks, we need to say that either student used the Newton balance or student used the normal balance and multiplied mass by gravity. How did the student find the center of gravity of the meter stick? This asks you to recollect when you carried out this experiment in your labs. And if you remember, one of the steps in the experiment was finding the center of the gravity of the meter stick. And the meter stick, to find the center of the gravity of the meter stick, what we had to do is we had to hang the meter stick from a thread or something like a thread, and then move the meter stick within the thread until both sides of the meter stick are balanced. So they don't move neither up nor down. So when both sides are balanced, that location, the particular location on the meter stick right here in the center, is where the center of the gravity of the meter stick is. And then the last question is, how did she make sure that the meter stick was balanced and level? We have 2 different parts to this question. That's why we have to be very careful that we answer both of them. So how did we make sure that the meter stick was balanced? Balanced means that the meter stick doesn't move. So forces on the one side and force on the other side, up and down, left and right, are kind of all equal. So meter stick is balanced when the meter stick doesn't move. It's very simple. So you were hanging weights until the meter stick wasn't moving, and that's how you made sure that it was balanced. And level, there are 2 ways to do it. One is simple, just use your eyes and state that you check that the meter stick is visually level. The second one is to use a spirit level. So you put spirit level on the top of the meter stick and check that it's level looking at the bubble within the spirit level. So that's how you make sure that the meter stick was balanced. Next part of this question asks us to redraw the above diagram in the answer book and include the weight of the meter stick above. Now, you need to remember the following. Weight is a force, so force has magnitude and direction. We know from reading the problem is that the weight of the meter stick, let's call it W, is equal to 2 newtons. So that needs to be included in the problem. And also we know that the weight is at 50 centimeters mark. So the thing to do here is to find the 50 centimeters mark, which is over here. And now we need to draw a force. The important thing to remember is weight is a force that always acts down towards the center of the earth in this case. So we put the force at 50 centimeter mark, we draw the arrow down, and we add 2 newtons to the force for full marks. Last part of question 1 asks us to consider laws of equilibrium. So the first law of equilibrium states that the sum of the upward forces equals to the sum of the downward forces. Using appropriate calculations, show that the first law of equilibrium is verified in this experiment. So we know that the first law of equilibrium is looking at forces. So let's take a look at forces that we're considering in this problem. Downward forces, let's look at them first. We have 3 newtons at 30 centimeters, 2 newtons at 50, and 7 newtons at 70. So we have 3 plus 2 plus 7 equals to 12 newtons. Upwards, we have 8 newtons at 40 centimeters and 4 newtons at 90 centimeters. So the forces acting upwards are 8 plus 4 equals to 12 newtons. Here we can see that downward forces are equal to 12 newtons and upward forces are equal to 12 newtons, which says that the law of equilibrium is verified. Let's write down up equals to down, and we get full marks. And the last part of this question asks us to check whether the second law of equilibrium is verified in this experiment. So the second law of equilibrium states that the sum of the clockwise moments equals the sum of the anti-clockwise moments. Using the 0 centimeter mark on the meter stick as the fulcrum, the calculations for the clockwise moments are given below. In your answer book, complete the calculations to verify the second law of equilibrium. So what is a moment? A moment is a physical quantity that tells us something about the rotation of an object. And in this case, we know that our fulcrum is over here. It's at 0 centimeters. To calculate a moment, moment m, is equal to force times the distance from the fulcrum. So we know that if we know the value of the force and we know the distance from the fulcrum, we can calculate the force. So let's take a look at the clockwise moments. Clockwise moments rotate the ruler in a clockwise direction. Which forces are those? Well, the first one, if you imagine that there is this is the center of our clock, the force at 30 centimeters will rotate our ruler in this direction, which is clockwise. Second force that will rotate it clockwise is the force over here. And the third force that will rotate our ruler clockwise is the force of 7 newtons at 70 centimeters. So to calculate the clockwise moments, the examiners took the force of 3 newtons at 30 centimeters and used our formula to find that moment, adding the force of 2 newtons at 50 centimeters, 2 times 50, and 7 newtons at 70 centimeters. So all you need to do is to verify that this is correct by finding the counterclockwise moments. Which forces give us the counterclockwise moments? Well, the force at 40 centimeters acting up and the force at 90 centimeters acting up. So they would rotate the ruler in this direction, which is obviously counterclockwise. So what would be the moments acting counterclockwise? Moment 1, well, I call it M1, is equal to 8 times 40, which is equal to 320 Newton centimeters. Moment 2 is equal to 4 newtons acting at 90 centimeters. So 4 times 90, which is equal to 360. So the law of equilibrium states that the sums of the moments are equal. So let's find what's the sum of the moments acting counterclockwise. We have 0, 8, 6, 680 Newton centimeters. Let's check that this matches. Yes, it does. So I just filled the rubric in our table to get the full marks. (680 Newton centimeters), the final answer. This series will continue later on with questions 1 through 8 or 9. If you have any questions, you can find me on Twitter at Mr. Oziak, and hopefully you'll find this video useful. So thanks for watching, and until next time.